This is the first lecture for Module 8 in the book Problem-Solving Guide for Electromagnetism and Optics, the source of the magnetic field. In Module 1, we looked at electric fields produced by electric charges. In the previous module, we considered the magnetic force on a charged particle moving through a magnetic field. But what is the source of the magnetic field? What causes a magnetic field? It would be nice if we could say magnetic fields are produced by magnetic charges, but this is not the case. In this universe, there are no magnetic monopoles, no magnetic charges. Magnetic fields are produced by moving electric charges. This relationship was discovered accidentally by Hans Christian Ørsted giving a demonstration in an evening class with a current. When you turned on the current, a compass needle nearby was deflected. And he says, what's up with that? Previously, electricity and magnetism were completely different phenomena. They were considered to be independent phenomena. Electricity was static electricity you could get by rubbing amber on fur, for example, or lightning. And we've known about magnets for a long time because there are magnetic rocks. Here's a piece of lodestone and with magnetite in it, and there's nails stuck to it, and it looks like just magic. Why would these nails stick to a rock? And what does it have to do with lightning? In this module, we're going to focus on magnetic fields produced by currents, charges moving in wires. We're going to start with a long straight wire carrying a current I. There it is. First, we're going to talk about the direction. Then we're going to focus on magnitude. The magnetic field is a vector. It can be thought of as a series of concentric circles around the wire. So we can put them in. If I put a compass at the top above the wire, it's going to be pointing into the page. If I put one below the wire, it's going to be pointing out of the page. You can determine the direction with the right-hand rule. A different right-hand rule, stick your thumb along I and curl your fingers around the wire, and that's the direction of the field. At the top, it's going into the page. At the bottom, if it's coming out of the page. That's the right-hand rule for the direction of the magnetic field produced by a current. To get how big it is, how strong the field is, we need to use integral calculus because this part of the current is contributing much less to the field here than the current right next to it. We have to sum up all of those contributions. The complete derivation is given in the text. We're just going to give the result here. Here's the geometry. Here is a little current element di. It produces a little infinitesimal vector directly into the page, dB. And each one of these di's produces a field. The field's getting bigger and bigger and bigger. As I go right underneath it, it's the biggest, and then over here, it's getting smaller and smaller. If I add up all of those contributions from every current element, I get the total magnetic field, B. Here's the integral. Mu naught I over 4 pi A integral sine theta d theta from one end of the wire to the other. Mu naught is the permeability of free space. It's 4 pi times 10 to the minus 7th newtons per square amp. Little a is the perpendicular distance between the wire and the point at which we're measuring the field. And theta is shown in the diagram. It's very important to understand theta, and we're going to do a lot of work with it. Here's the result. Mu naught I over 4 pi A times the difference in the angle, the cosine of the angles between the ends of the wire. Here's what it looks like. Here's theta 1. Here's theta 2. The wire ends here and here. If the wire is long in both directions, it goes all the way to the left, all the way to the right. The longer the wire is, the bigger theta 1 gets to 180. And the bigger theta 2 gets to 0. And most of the contribution to the field is underneath the point, right in here. Once you get way out here, this little current element doesn't produce much field at all here. So it doesn't have to be really long for this to be a very good approximation. So now I can stick in 0 for theta 2 and 180 for theta 1. And cosine of 0 is 1. Cosine 180 is minus 1. So 1 minus a minus 1 is 2. And that's what this 2 is over here. If the wire is infinite in both directions, this factor, mu naught I over 4 pi a, is 2. If the wire is half infinite seems like a silly term, because if it's infinite, it's infinite. What's half infinite mean? Well, it means that it starts at A, right underneath the wire, at the perpendicular distance, and then it goes all the way out. So here, theta 1 is 0, theta 1 is 90 degrees, and theta 2 is in here, and that's going to be a very small angle, 0. And if we plug those angles in, we get cosine of 0, which is 1, minus cosine of 90, which is 0, so there's a 1 there. The factor is 1 for a half infinite wire, and it's not surprising that it's half of a wire that's infinite in both directions. Now, it's also true that the distance between the perpendicular distance, there doesn't have to be any wire there, like this. Here's the wire. There's no wire underneath the point, but the perpendicular distance is still A. You have to carry the wire straight in both directions. There's a little dotted line here. So that A is the perpendicular distance, and then there's theta 1, there's theta 2. Now, the second geometry we're going to consider is the center of a circular arc. Each current element, dI, produces an element of magnetic field dB out of the page. So here's all the dI's going around. And if I use the right-hand rule and stick my thumb to the left, my fingers curl out of the page underneath. So dB is out of the page. The integral here is trivial because every dI makes exactly the same contribution. R is perpendicular to dI. It's not the case with the straight wire. The angle's changing all the time. The wire is always perpendicular to the radius. So all you have to do is sum up all the di's, which means summing up thetas. So this theta is the arc. It looks like maybe 120 degrees of arc. The arc of the wire itself. To understand that, let's just look at a complete circular loop. What's the angle of a complete circular loop? Well, it's 2 pi. So I have mu naught I over 4 pi r times the angle of the loop. That's one circle. If it's a half circle, the angle is pi. If it's a quarter of a loop, it's 90 degrees. Pi over 2. You have to use radians for the angle here. So the problems usually involve the magnetic field produced by some combination of arcs and wire segments. Here's one. There's a straight part of the wire, then there's an arc, then there's another straight part of the wire. And here's the point where we want to determine the field. What's the magnetic field here due to the current in this wire? We'll call the current 500 milliamps. There's a 90-degree arc. So if I look at this arc, that's a quarter circle, 90 degrees. What's the magnitude and direction of the magnetic field at the center right here? It's important to understand that this wire, remember how the field lines look. Can you picture them? They're circles around the wire. This wire has 0 perpendicular distance to this point. The field is on the side, it's not in front of it. This wire makes no contribution whatsoever to the magnetic field here. There's magnetic field up here and down here, but not here. So we can ignore this part of the wire when it comes to calculating the field here. Now we have an arc. If I stick my thumb in the direction of the current, I see that it's producing a field into the page here. So this arc, the magnitude of that field is mu naught I over 4 pi r. That's the factor, and there's the angle, 90 degrees, pi over 2. I can calculate that. Mu naught is 4 pi times 10 to the minus 7th newtons per square amp. There's the current. I converted it from milliamps to amps. And the radius of the arc is 10 centimeters, which is 0.1 meters. And there's the angle of the arc. And I can get 0.785 microtesla. And that's just from the arc. Now we got to consider this wire up here. This is half infinite, doesn't go to the left, it just goes to the right. This angle, if I draw that line straight up, that's 90 degrees. So one of the angles is 90, and one of them is 180. Cosine of 90 is 0, so I get a 1 here, half infinite. And all those prefactors are the same. That's a half a Tesla, half a microtesla, and it's in the same direction. If I stick my thumb in the direction of the current for this straight part of the wire, the field is into the page. The magnetic fields are both into the page. They add from the arc is 0.785 microtesla. From the straight piece of wire up here, 0.5 microtesla, add them up, and I get 1.285 microtesla, and I have to say the direction into the page. As with electric fields, there are problems that ask for the point where the magnetic field is 0, and problems that involve adding magnetic field vectors. That's the subject of Lecture 2.